So this is our first probably long derived rule, or one with a long proof. And I mean, other than the ones that I skipped. And this one is called DeMorgan's law. So I think of this as telling you how to distribute a knot. So if you have a knot and you want to distribute it over, say, an and, then you can, but it flips this around. So you get not phi or not psi. And it's pretty easy to make this intuitive for yourself if you just think about filling in some propositions for phi and psi. And so this is just one version of it. There's another version where it's all about distributing the knot over an or instead of an and. And I think I'm going to make the other version one of the presentable problems if you want to present for your second presentation. Okay, so here's one version of DeMorgan's law, and it's an if and only if. It's an equivalence. Remember, our main limitation is that we're only allowed to use the rules that we've established, that we've laid out, and the previous derived rules. So things like alternative eliminated we're allowed to use. That's a derived rule that we've already derived. But also like proof by cases, proof by contradiction, those are the things that are available to us. As well as basic things about and or. For example, here there are some basic rules, like if you have phi and psi, then you can deduce phi and you can deduce psi individually. If you have phi or if you have psi, then you can deduce the disjunction. You can deduce phi or psi. So those are like basic rules that we have available. Okay, so what we're working on here is a certain kind of if and only if. So there will be two halves to the proof. So let's start with the first. Now I get to assume the left side and I need to prove the right side. So assume that it's not the case that phi and psi. And now the goal, we must prove that not phi or not psi. And now I'm immediately stuck, kind of. I'm stuck because my basic rules for proving an or like this are to prove one of the two sides of the or, right? So if I'm going to prove this, I need to either prove this, and then I can deduce the or I prove this, and then I can deduce the or. But I don't feel like I can do either of those things. Let's say phi is I am tall, and psi is I am happy. Then my assumption is saying it's not the case that I'm both tall and happy. And then I'm trying to prove that either I'm not tall or I'm not happy. But if it's not the case that I'm both tall and happy, then I don't think it's possible for me to prove that I'm not tall. Because I might still be tall, right? I might just be not happy. And similarly, I don't think it's possible that I'll be able to prove I'm not happy. I might still be happy and just not be tall. So I don't feel like I can prove either of these individually right now. So this really takes some thought at this stage. And one thing that helps push us forward is excluded middle. So excluded middle says that things are either true or they're not. Everything is either true or it's false. So for example, if I imagine that these are phi is I'm tall and psi is I'm happy, then if it's not the case, I know here that it's not the case that I'm both tall and happy. Well, excluded middle says I'm either tall or I'm not, right? I'm either tall or I'm not. So if I'm tall, then I think I should be able to prove that I must not be happy, since I'm not both tall and happy. And if I'm not tall, well then I'm not tall, so I've already proven one of the two sides of the or. So an excluded middle can help here. But I admit that this takes a while to think about at this next step. So it might seem like it's coming out of nowhere. So due to excluded middle, either I'm tall or I'm not, phi or not phi. This can drive a proof by cases. A proof by cases is kind of what I just described verbally. Suppose I am tall. In case 2, suppose I'm not tall. Well, case 2 is easy. Let's get that done. If I'm not tall, then I'm either not tall or I'm not happy. So I'm done. That's just using the basic rules of OR, which say if I have something, then I have that thing, or, and then I can put whatever I want there. And yeah, so just to clarify, what I'm using is this, the basic rule for OR, which is saying I can deduce the OR from either one of the two disjuncts, or whatever you want to call these individual things. So that's done. But case 1, suppose phi is true. So suppose I'm tall. And we know that it's not the case that I'm both tall and happy. But I know I am tall. How can I prove that I'm not happy? Well, here's one way to think about it. If I were happy, considering that I'm tall, if I were happy, then I'd be both tall and happy, which is exactly what we're assuming I'm not. I hope that makes sense. So why do we think that if I'm tall and I'm not both tall and happy, that it follows that I'm not happy? If I were happy, then I'd be both tall and happy in this situation. And that's what we're assuming is not the case. So that sounds like a proof by contradiction. So inside case 1, there's going to be a little proof by contradiction. And I'm just going to box it in, but you can just kind of make it its own paragraph in your writing. Maybe indented inside of case 1, or just underneath case 1, but before case 2 starts. So suppose, for the sake of contradiction, that I am happy. This is kind of a grim proof. Suppose for the sake of contradiction that I'm happy, then phi and psi is true. And this is our contradiction. We have phi and psi and not phi and psi. So that means phi and psi and not phi and psi. And this is a contradiction. Anytime you have a proposition and not the same proposition, that's what a contradiction is. So this is a contradiction. Therefore, we can end the proof by contradiction. So we can say, therefore, sometimes I like to put the end of the proof by contradiction outside of the proof by contradiction. I feel like that makes sense. So if I'm going to box things in, which you have there's no need to box things in, but if I'm going to box in the proof by contradiction, then I'd rather put this outside and say, therefore, what I assumed for the sake of contradiction, psi, that I'm happy, must not be true. Okay. Now suppose I'm not tall. Oh, we already did this. Yeah, so this one is done. Are we finished? I feel like we're not finished. The goal is in each case to reach this. So in each case we need to reach the end goal. And I've done it in case 2. I think I'm missing a step in case 1. I should say at the end, since I've now proven not happy, I'm either not tall or I'm not happy. Thus, not phi or not psi. Okay, so now you can see case 1 ends with the thing I need, case 2 ends with the thing I need, so I'm done with this part of the proof here. So that's half the proof. Let's work on the other half. Let's see. So now I get to assume not phi or not psi. And the goal now is to prove, so let me make it clear, we must prove that it's not the case that phi and psi. So I'm assuming that I'm either not tall or not happy, and I must prove that it's not the case that I'm both tall and happy. Now, this direction here I think is a lot easier than the previous one. I've got an or to work with here, so I don't need to come up with some cleverly chosen excluded middle to drive my proof by cases. I have an or. I can just start with my proof by cases. Case 1. So I know I'm either not tall or not happy. So suppose I'm not tall. And then case 2, suppose not happy. So let's see. The goal is to prove that it's not the case that I'm both tall and happy. If I know I'm not tall, then can I come up with an argument that I can't be both tall and happy? Well, if I were both tall and happy, then I would in particular be tall, but I'm assuming I'm not that. So that would be a contradiction. This is a proof by contradiction. So here is a proof by contradiction that I'll box in here. So suppose, for the sake of contradiction, that phi and psi, that I'm both tall and happy. So I'm assuming this because I want to prove its opposite. Then I must be tall. But then I'm both tall and not tall, right? I'm tall because I assumed I'm both tall and happy, and I'm not tall because I assumed that for case 1. And there's our contradiction. Thus, I must reject what I assumed for the sake of contradiction. So here's the thing I needed to reach, and I have reached it in case 1. And hopefully I reach it in case 2 at the end here. And you can imagine case 2 is going to look really similar. So let me just copy and paste actually. Here we are. And it looks like I lost the S here somehow. Suppose for the sake of contradiction that phi and psi, then, and now the actual contradiction I'm going to get has to do with psi. Then psi, so then I have not psi from the assumption for case 2, and now I have psi, so there's our contradiction. And that's it for case 2, and that's it for DeMorgan's law. So I'll put my box at the end. So we just got done with derived rule 16 here, DeMorgan's law 1, and then I've got DeMorgan's law 2 down here. And I think I'm going to make this one a presentable problem. Let me show you a quick way to do it, which is interesting. So here is DeMorgan's law 1. This is the one that we just got done proving. And it's supposed to apply to any proposition, phi, psi, phi, psi. If you take any proposition, phi and psi, and you fill them in here, then that works. That's how all of our rules and derived rules work, right? They involve these proposition placeholders, and the reason they're placeholders is because they can be replaced by any proposition you want, and the rule should work. So instead of phi, I'm going to put the proposition not phi, where phi is possibly some other proposition. And instead of psi, I'm going to put not psi. So this is supposed to work no matter what propositions I put in for phi and psi. So I choose to put not phi in place of phi, and not psi in place of psi. then the left side of the double arrow looks like this, and the right side of the double arrow looks like this. And we already know that if we see a double negation, then we can just erase it. Or to be more precise, not phi is equivalent to phi. Not phi holds if and only if phi holds. But more or less, that allows us to just remove these. So let me simplify what the right-hand side looks like. It's just phi or psi. Now, this is an equivalence, and we can always negate, or invert, I think I called it. We can always invert an equivalence. That was this rule here, derived rule 15. If you have an equivalence between two things, then you can stick negations on both things, and you have that one too. So now negate both, and what do you get? Let me move this to the right. Now negate both, so negate and negate. So here I have a double negation, so I can erase that. And there is DeMorgan's law number 2, or that's what I called it in the notes. There's the other version of DeMorgan's law, which tells you how a knot will distribute over this OR. So this is one way to do. This is one way to prove derived rule 17. I didn't write it very carefully, but that's one quick idea where you start with DeMorgan's law, and then you invert the equivalence, and you just apply it to negated versions of phi and psi. What I want you to do for your presentable problem, if you choose to present it for presentation 2, is try to do this, but without using DeMorgan's law 1. So you can use the ideas in here if you want to, but try to come up with a proof and present or explain your proof without relying on DeMorgan's law 1, so without relying on that trick. So just using the basic things like how to prove an equivalence, how to work with or and those kinds of things.